Very honored to speak here, especially to start this fabulous cast of speakers later in the day. And I will actually, I realize I'll probably connect to all of them in my presentation here. And I added a couple of words to the title, Quantum Computing with Atoms and Optics. And if I were to cut to the chase, I would say that the qubit part, the quantum part's done. And those are the atoms. They're atomic clocks. And I say they're perfect, meaning they're much better than we need them to be. All of the challenges remain in the classical controllers, and that in our technology means optics. So this is a picture of a semiconductor, a chunk of silicon plated by gold. That's part of the controller. These are just electrodes that allow individual atomic ions to hover, float above this ion trap. And they're glowing because we're shining CW laser light on the atoms and they're fluorescing. And the control of them has other lasers that execute quantum gates. And I'll dive a little bit into that technology. But first, since this is a talk on quantum computing, I thought I would start on very broad tones, defining terms and so forth. And this may sound a little overhyped, and I don't want to stress it that much, but the high-performance computing community is running scared a little bit now because we all know that Moore's law will not continue forever, at least how it has over the last many decades, because the individual transistor elements are getting too small. And we can see even in the last few years it's starting to saturate. There are many other forms of computing that are starting to make the light of day, neuromorphic computing and so forth. Quantum computing is one of them, and it's not exactly clear that this what the coverage of quantum computing will be. But I put this plot up here because in the days when Moore's law started were early days of transistor development, solid-state transistor development. And one Richard Feynman was intrigued by the fact that computing elements could be built from solid state. And he imagined the day when they could be shrunk down so small that each transistor is a few molecules or a few atoms. And that's where we'll be. And if we follow Moore's law now, that's where we'll be in the next couple of decades. But what Feynman said in this lecture in 1959, incredibly visionary, he said, when we get to circuits of individual atoms, there will be completely new opportunities for design. And I think at that time, it wasn't known what those opportunities would be. I think by now, over the last few decades, we understand that opportunity is quantum computing. And the reason there's new opportunities, of course, is that when you get down to simple forms of matter with very few degrees of freedom, the laws of physics change. And those laws of physics, quantum physics, may allow us to compute in new ways, and that's the opportunity. So very briefly, most of you, this is probably a review for most of you, but quantum bits are very much like classical bits, zeros, ones, except because of the quantum superposition principle, information can be stored in parallel, even at a single bit level. So a quantum bit is a superposition of 0 and 1, and it's very hard to draw that because we live in a classical world here, and this is a classical projector. But that's a single electron, of course, in two states at the same time. And it has weightings of the two states. And there are lots of ways to couch the strange opportunities of quantum. One of them is that when you measure a quantum state, you have to use probabilities. Probabilities have to be invoked. They come out of thin air. In other theories of nature, probabilities are used because of our ignorance, but in quantum mechanics, you have to use it. So that's one strange feature of quantum mechanics. And so what happens, of course, is that the state collapses to one of two definite states depending on the weightings of the original superposition. Now, it gets interesting when you put many qubits together, even two. There's something called quantum entanglement. And in this case, this is a particular entangled state of two quantum bits. And you can see when you measure such a system, you'll see one of the two states with perfect correlations, even though individually they're totally random. Okay? So the concept of entanglement is in a sense, having connections or wires without real wires. It's due to the structure of quantum mechanics. And that, to me, is the essence of quantum computing. We're using connections that aren't there. Should say that with quotes, because there's lots of subtleties involved in that. So the story of quantum computing and where it came from and And how you could do something interesting is it's a very subtle one, and I'm not going to be able to touch on a whole lot of it. I like to think of it as a good news, good news story. And the first piece of good news might be apparent from this. The fact is that we get exponential growth in storage when we add qubits together. With 3 qubits, there are 8 states you can store. With lots more qubits, you get this exponential growth. Every additional qubit gives you twice the state space to store information if you want. And for instance, if you wanted to compute a function, you could do it in parallel with the same device with only one input, but the input has a superposition of all the numbers, okay? And because it's exponential growth, it doesn't take too much scaling to get something you could not think of doing without quantum. With just a few hundred qubits, you're representing a number of configurations that's more than the number of fundamental particles in the universe. So even with Moore's law, even if Moore's law were to continue forever, you still would not be able to approach what you could do potentially with a quantum computer with just a few hundred qubits. That's the great good news. It's almost too good to be true, and it is. When you think about a computer, you have to measure it, of course, and when you measure it, that's the bad news. And the more complex the superposition, the less information you get out, right? If you have 2 to the 300 inputs and you make outputs and you make a measurement, you only get one answer, and you don't know what it was. It's random. So that seems very bad. I'm sure Feynman realized this in '59 and didn't know how to put it together. But in fact, 20 or 30 years ago, there is a final piece of good news that was, I would say, codified more by David Deutsch than anybody else. And he showed that there are cases where you can have interferences between these amplitudes. It's very hard to draw. But if you imagine all these inputs in superposition, these red dots are called quantum gates. They allow very specific interferences to occur, entanglements to be formed, and so forth. And what happens here is you have this exponentially rich input state. It sort of gets forced down to one output or a few outputs. And that you can measure. You can measure, and there's very little entropy in that output state. And the point there is that when you make that measurement, in some cases, it can depend on all of these exponentially many inputs. Okay? So that's the basic idea of quantum computing. And I'm sweeping a lot under the rug because not every problem can be stated this way. What type of gates do you need to do something interesting? Well, there are a few applications out there. I would say the killer app in quantum computing, as you might know, is factoring large numbers. And this is pointed out by Peter Shor about 20, 25 years ago. And he basically showed how you could build a quantum circuit with a polynomial number of gates that would allow you to factor a big number. And what's remarkable is that classically, the best known algorithms still scale exponentially with the size of the input. And so very, very broadly, what he showed is that you could take a quantum wave function with lots of states. This would have like 6 or 7 qubits, whatever log base 2 of 39 is. Maybe you need some more workspace. And execute quantum gates so that the wave function does this. It sort of coherently evolves to the 2 factors of the number you're trying to factor. And then when you make a measurement, you can get information on all those inputs. So that's factoring. And I would say the problem with factoring is that to factor an interesting number requires thousands of bits. You probably need error correction because you need billions of operations. And this is sort of like an analog computer. The noise will add. So you have to do error correction. So you probably need trillions of operations and millions of qubits. So this problem is still far in the distance. It was back in '95 when I first got in this field, and it is now. It feels like it's the same distance away. But the good news is there are other problems that are, I would say, even more interesting and more widespread than factoring that have the flavor of having an output that globally depends on inputs. So optimization is a little bit of a catch-all. But when you optimize a very complex function, there's only one optimal answer, or very few numbers of answers, and they can depend on all the inputs. This is a simple one. If we have a function of just 2 variables, we can clearly see the minimum. But if you have a function of 1,000 variables, the configuration of those variables that results in the minimum or the maximum, minimizing some cost function, that's a really hard problem. And there are all kinds of combinatoric optimization problems from finance, from physics, from chemistry that look very interesting for quantum computers to solve. Now, that said, we don't yet have a proof that any one of these applications can be exactly solved on a quantum computer. But there are hints that quantum computers could be a heuristic that gives you a better answer than any classical approach could be. The traveling salesman is my favorite because it's very easy to depict. What's the shortest path between a bunch of cities? And the problem here is there's too many configurations once you get a few hundred cities. And so that type of a logistics problem is, I think, where the field is headed. And it's good because this is more broad than just factoring. So I want to talk about hardware because it's an exotic form of computing and therefore demands pretty exotic hardware to do the job. So my colleague Bill Phillips is fond of saying that a quantum computer differs more from a classical computer than that classical computer differs from an abacus. And what he means here is that these two machines follow the same abstract theory given by Alan Turing. They're both Turing machines. One is electronic, built with transistors. It's very fast, and you can have trillions of transistors here. But they're the same rules. Quantum computing is a totally different set of rules. And so I guess I would say a corollary to this statement is that why would we ever expect a quantum computer to look anything like a classical computer if it's that different? And so that's why we have to maybe step back and look at anything that supports quantum coherence, anything that we use in quantum research to think about building devices from them. So the last 5 or 8 years have been very exciting in this field, primarily because we're starting to see systems engineering, quantum systems engineering, building a device that a third party can use without knowing every detail about what's inside. We need an application, but maybe we need a device first that somebody can use that might not be an expert in quantum physics to use it. So superconducting qubits is one path forward where superconducting currents, they flow without dissipation. So it's a perfectly interesting qubit to think about. The scale-up problem looks very hard because every qubit's a little different. They're man-made. And I would say the leading candidate is maybe even more exotic or less looking like a classical computer. It's not solid state at all. Individual atoms. And this is what I want to talk about. And the opportunities with atoms are manyfold. One of them is that atomic qubits they're identical. They're not man-made. They're given to us. So these atoms are atomic clocks, and they have the same features that atomic clocks have in terms of their longevity, their coherence, and so forth. And like I said at the outset, the challenge is how to control them, how to make gates, how to hold on to them and isolate them from the environment. So I want to talk a little bit about that. And I'll note also that industry is getting involved in this field in a big way, mostly with these two technologies. There are a few others as well. And these are very well-heeled companies that are especially computer companies like IBM, Intel, Microsoft, and Google that are looking to next new models of quantum computing, and a host of startups. Of course, the government here in the US, I've listed a few of the big investments. Some of them are in the intelligence agencies, Department of Defense, Department of Energy, and so forth. So now turning on to this technology of individual atoms, dive into a little bit of atomic physics. We store our qubits within individual atoms very much like 2 levels are stored in an atomic clock. So pick a good 2-level system that is insensitive to external perturbations like nuclear spins, something like this, and that's a potential qubit. Now, atomic ions are very interesting because they interact very strongly through their Coulomb force. I'll tell you a little bit how we harness that. Again, because they have very low idling errors, almost 0, and they're perfectly replicable, the atomic systems are scalable, fundamentally scalable, in a way that no solid-state system could ever dream. Okay? Now, it's interesting that to control these atoms, we need optical sources, we need lasers to do this, and this is 100% of the challenge in the technology I'm dealing with. So to give you a little idea here, and also there's a little bit of history in this picture. The atomic qubit that I've been investing in for a long time is atomic ytterbium. It looks a lot like hydrogen, actually. Spin 1/2 nucleus and 1 outer electron. And so there are hyperfine levels, and we store our qubit in these so-called clock states of this ion. And we drive coherent transitions with a pulsed laser. And the history there is, I come from the field of cold atomic physics, CW lasers, with 11 digits of stability on the wavelength. So my whole life up till when I went to Michigan in 2000, I was very scared of pulse lasers. And you know, it's nice to speak in the same session that Donna and Gerard are, and I'll add that Phil Buxbaum, my colleague in Michigan, they got me less afraid of pulse lasers. And I have to say that this particular band of pulse laser at 355 nanometers, I'm sorry it's not femtoseconds, 10 picoseconds. It's too broad bandwidth for us at femtoseconds. But this laser is very much like a CW laser. It's so well engineered because it's used for lithography. It's an industrial standard. Coherent makes several hundred of these a year. And even though I love playing around with lasers, I used to do that a lot, I'm happy that this laser only has one knob, and it's the on knob. And that makes this a system. This laser runs for years and years without thinking about it. That's very important. And it has all the coherence we need. It actually is sort of a frequency comb, a narrowband frequency comb, that I won't talk too much more about it, but we're able to coherently drive this qubit and apply forces with this kind of a laser beam. And yeah, it's a pulse laser. Not super high power, but OK. So I want to show a little animation on how we build a small register of qubits and entangle them, involving this type of a laser and CW lasers. So the idea starts with a bunch of laser beams. This is a multi-channel AOM. We'll talk about that later if you want. And these laser beams are all fed across this chip. Now, we first initialize all these qubits with a CW laser that does optical pumping. And then we execute a quantum circuit. So this is space and time. We're going forward in time. Now, these lasers, these 355 nanometer lasers, are basically optical tweezers. And we're going to hear from Art Ashkin via video on the physics of that. We're driving forces between these atoms. And that's how we can couple the information and execute quantum gates. And this is a small quantum circuit that executes some computational task. And at the end of the day, we send another CW laser for measurement. And it's a very simple measurement. If the atom glows, it's in 1. If it's dark, it's in 0. So that's it. A lot of optics here. In fact, that's, as I said many times now, that's 100% of our challenge, is the optical controller around these perfect qubits. So this is an example of an algorithm, a very small one. I won't get into details too much. It involves 3, 4, 5. This is 10 qubits, and it has, I don't know, 50 or so operations. These are Hadamard gates. These are Ising gates, controlled Z gates. I won't get into the details, but this is a quantum computation. It actually is an algorithm. It's called the hidden shift algorithm. It's an oracle algorithm. It's sort of useless, but it's a benchmark demonstration. If you have 10 qubits, you might think of measuring the fitness of your system running this algorithm. It says if you're given 2 functions, and they're identical except the inputs are shifted by some unknown amount, what is that unknown amount? How many queries do you have to make of these functions to find the unknown amount? Well, classically, you need a lot. You have to evaluate many inputs to figure this out. But quantum, you can do it with just one query. So you can see both the interesting thing and the useless thing. I mean, nobody's going to give you a quantum computer and tell you what's the hidden shift here. But it's interesting because it does give you, in a sense, an opportunity you could not do classically. And so, this is the initialization, the gates, and then the measurement at the end. And here we programmed all 1024 hidden shifts. 2 to the 10th is 1024 on the vertical axis. And this was the measurement. If things were perfect, we would have had a 1 on the diagonal here. But you can see there is some noise. It's very structured noise. If you look closely, you can even see little circles here and these lines. We understand these noise. They have to do with crosstalk and imperfect laser noise and so forth. But we understand the entire error budget in this algorithm, and we're working on building more. And I should say this comes from IonQ, the startup that has 3 full-stack quantum computer systems right now. Now, back to the University of Maryland, we have several systems that we're also building up. This is a little bit more of a physics experiment, but with lots and lots of qubits. And what we've studied there is not a quantum computing circuit, but what we might call a quantum simulation. And in this case, we were able to apply a Hamiltonian that is an Ising model between all pairs of spins, and it's a long-range Ising model, and it's antiferromagnetic, so it's frustrated. There's lots of entanglement in the ground state of that Hamiltonian. And we have a transverse field. So this is a very simple textbook model of something that admits a phase transition. In this case, we've been studying something called a dynamical phase transition, and it has to do with the competition between B and J. If the spins are prepared along X, and the Ising coupling is very big, they're already along the X direction, so nothing very exciting happens. But if B is much bigger than J, then they precess around the Z axis. So do they stay around X, orbit around X, or do they precess around Z? And by varying B and J, we can sort of see different dynamics. Again, sorry, I have to kind of rush through this, but this is the total magnetization, the brightness of the chain. And you can see when B is small compared to J, not much happens to the initial magnetization. But when B is bigger than J, they sort of go to 0. They precess around Z. And I would call that a phase transition. It's a very smooth transition between these. And I think this is with only 16 spins or something. We can now look at the correlations. We measure every possible correlation of these spins. And this is something that you can't do in a real solid. And now as we vary the number of spins and vary B over J, we see sort of a dip emerging, but it's still, even up to 53 spins, where there are 2 to the 53 configurations, we don't see a real pronounced dip. But when we look at the n-body correlation function, in this case, we're looking at the size of the biggest domain in the system. As we vary B over J, we see a much more pronounced kink here. And I will say that we couldn't compute where that kink was going to be. The system is too complicated. So I'm not claiming this is a real model of a real material, or it's even interesting, but it's something you could not compute using classical physics. So to me, that's kind of interesting. So how are we going to scale? And I would say in the atomic physics realm of quantum computing, it's often said, well, with transistors, we can print 1 billion of them on a chip. Even with superconductors, we could think of how to print thousands and thousands on a chip. But with atoms, you're showing me data with 10 qubits or 50 qubits. How are you going to really scale? Well, the scaling, in a sense, we have the fundamental ingredients, because when we add an atom, we know it's the same. It's all a question of controlling it. From the trap itself, we have to make the trap big enough to hold these atoms. And one way to scale beyond 10 or 20 qubits is to just add atoms. And you might say, well, now you need 1 million laser beams. Well, not really. You could imagine having a fixed set of laser beams and shuttling the atoms around the beams, very much like a tape moves across a head. There's some overhead there. You have to move the atoms around. But that's actually a very mature technology, shuttling atoms back and forth. And I would say Dave Wineland and his group at NIST Boulder, I was there in the 90s, we really pushed this vision of shuttling around corners and so forth. And at NIST, they're doing some wonderful experiments, moving atoms between different zones even. The technology that needs to improve there is the ability to make chip traps that are more agile. They allow us to do many more things. None of this is quantum, though. This ion trap is it's a bunch of conductors that hold voltages, and we have to control those voltages. Now, when we want to scale beyond hundreds of qubits, and this is where it gets really wild, we're going to almost certainly have to adopt a modular architecture, just like we do with multi-core classical processors. And the great thing about atomic qubits is that they're optically active. We can map the qubit from the clock state, the spin, to properties of a propagating photon, polarization or color, or maybe a delay, many degrees of freedom there. And we can think about inventing a very high-level architecture where individual modules of ion traps with dense connections inside these red boxes are augmented by photonic connections, and everything over here is classical. This is just a non-blocking n-by-n cross-connect switch. You can build this. This is a CCD camera. These are beam splitters, and for instance, when 2 pixels on this CCD fire, that means, depending on the configuration of this switch box, that qubit is entangled with that qubit. So it's a modular architecture that allows you to scale. Now, what you sacrifice here is connectivity. Just like in the classical case, you can't easily do a gate between this transistor and that transistor. You have to move things around. That's certainly true, but it allows you to build the system up. And if it's modular, then you can really think of an industrial approach where you stamp out the individual modules. So there's lots of work that has to be done, and I think we look forward to having lots of on-chip photonic waveguides that allow us to move this information back and forth. So the real problem in the scale-up, and many people will visit our labs in AMO, and they'll see this, and they'll just say, OK, nice visiting you. So this table actually has 2 ion traps, but our first experiments were involving 2 atoms. They were about 1 meter apart, and we were teleporting the information between one atom and the other. We could actually say we teleported an atom, but it's, of course, just the information. It's 1 qubit. And it requires a great deal of control. A lot of these are CW lasers that have to be stabilized and locked to 9 or 10 digits. There is a pulse laser on the table. On this table, it's way over here. You can't even see it. and all the electronics. You can recognize these Toptica controllers. We love Toptica. And other laser companies are starting to modularize their lasers even. And on that note, and this is with very little exaggeration, everything you see here is in that box right now. This is a new project that we started a few years ago, largely funded by IARPA, and they funded us to build a small quantum computer system to do an error-correcting code, but it afforded us the opportunity to really design top-down. And so we've contracted with many outfits to help this make this happen, including Coherent, that makes the lasers. Harris, I didn't talk much about this 32-channel acoustic modulator. It's a beautiful device that Harris makes for the semiconductor industry, and we told them, you know, it's a beautiful device, but you need to be making it for atoms, not for CMOS masks. And they agree. And so we're partnering with them on this. The top guy mentioned AOSense as well, making individual modularized lasers that can be locked, all put in a drawer and fiber delivered. And finally, Sandia makes the silicon chip trap I showed before. And so this is starting to look like a product, and that's, of course, the story behind IonQ. We wanted to add professional engineering and not university engineering, which is a little bit of a oxymoron, I think, to do engineering so well that a third party could use a device. It's very hard to do that in a university setting. So there's the box. You can sort of see there's lots of cables. That's kind of ugly. These are CW lasers, all fiber pumped. These are FPGAs that are controlling the RF, the AOM channels, and the DC the electrodes on the trap. And there's a very agile software controller that runs all of this stuff. But the action's right here. This is where all the improvement's going to happen. And we look forward to making that even smaller. And inside there is the chip I showed earlier, the Sandia chip. There are many ways to make this chip. I didn't mention that the atoms are about 1/10 of a millimeter above the surface, and that's why it looks like a bow tie. We shine lasers across that surface. They focus tightly without hitting the sides. So that's what's going on there. Now, this plot I borrowed from my friend Hartmut Nevin at Google. He leads a Google quantum effort. And it's sometimes called the quantum supremacy chart. And what we have here is the number of qubits and the number of operations, the circuit depth. How many can you do? It's pretty clear if you have some number of qubits, you probably, to make use of that system, you want more and more operations. You want to be up and to the right. And in fact, if you're not sufficiently up or not sufficiently to the right, you're in this pink zone where it's not so interesting because we can classically simulate what goes on. If you only have, if you have 50 qubits, you better be able to do several hundred operations on them. If you have 1,000,000 qubits, but you can only do 1 or 2 operations, not interesting. If you have 3 qubits, but you can do 1 billion operations, not interesting. You have to do both. And with trapped ion technology, it's easy to speculate in the future, but the black data and the gray data, this is existing research, and we look forward in the coming years to pass through this so-called supremacy boundary. Whether there's going to be something interesting there or not remains to be seen. And when we get sufficiently high in qubit number and circuit depth, we have to do error correction. And with trapped ion technology, we don't worry about that yet because the passive errors are so good. We don't need to worry about error correction. We really think we can get in this land of treasure with several hundred qubits, several 10,000 operations with passive control. And what's a little bit of a disappointment, I think, what's happening in solid-state quantum computing is they're moving up and to the left. Maybe not a surprise. In a solid-state system, when you make the system big, there are many more types of errors that can come in. There's crosstalk errors, and the differences between qubits gets magnified when you have a big system. And the idle errors. When you leave a solid-state qubit alone, it dies all by itself because it's tightly coupled to its environment, the solid. The great thing in atomic physics is that these atoms, the background is a real vacuum. Some people may say, well, we're back to vacuum tubes. Well, quantum mechanics may demand that because there's very little the vacuum is perfect. There's nothing there. And furthermore, the optical controllers of these atoms allow us to reconfigure the program, and they allow us great flexibility in applying new types of algorithms. There's no wires between these qubits. So with that, I wanted to back out and talk a little bit about the big challenge ahead in this field, which is to do quantum engineering. And this is, since I work inside the Beltway, I get roped into working with the government on something called the National Quantum Initiative. And I for this audience especially, the Optical Society, SPIE, and the National Photonics Initiative played a huge role in Congress actually passing this National Quantum Initiative Act. And I show a picture here. Mike Raymer and I were sort of leading stakeholders. We formed this group across the country to lobby. And Laura Colton, who used to be the federal liaison at OSA, and now David Lang here, they've been tireless in getting us connected to offices in Congress. And this amounted to the NQI Act in December. Broad bipartisan support. The president signed it immediately. There are people from our community in the White House now that are advising NSF and DOE and NIST and also the defense and intelligence agencies on how to coordinate. Especially for this crowd, the goal here is to get optics engineers to start thinking about quantum. And so with that, I guess that's all I had to say. I wanted to put this joke up here. This is the cover of a tech review from last year that you could say quantum computing somewhere in here. There's a lot of hype in the field, but there's a lot of promise. And so very quickly, my group at the University of Maryland, funded by many sources in Washington, and the company IonQ, which I'm sort of stepping back from now. They're about 35 employees. And if you're interested in this and you're an optical engineer that wants to do quantum, please give us a call. We're going to probably triple in size over the next couple of years, and we're hiring aggressively. Thank you.